Question 3. We're told a horse has a natural ability to jump over obstacles. When it takes off, its horizontal velocity is 6.8 meters per second and the vertical velocity is 5.5 meters per second. Calculate the size and direction of the total velocity. Diagram may help, it usually does. So I would do something like this. That's our horizontal, there's our vertical, and therefore our total resultant velocity is that one. And we can put an angle in here since we have to find it. Now the vertical was 5.5 and the horizontal was 6.8. Okay, so that kind of diagram, helps you see what trigonometry you need to actually use. This is 90 degrees. So we can use Pythagoras to start with. 5.5 squared plus 6.8 squared, all square rooted, will give us the size of the velocity, total velocity v. If we do that, that gives us v equal to 8.7 meters per second. The angle theta can be found using the tan inverse of those two sides, 5.5 divided by 6.8. And if we do that carefully, we get 39 degrees rounded up to two figures. Okay, part B, this projectile question, we're asked to find the horizontal distance the horse travels while it's in the air. And you're told to start by determining the time the horse is in the air. Of course, if we know the time of flight of any projectile, then if we multiply that by the horizontal component of the velocity vector, which we were given before as 6.8 meters per second, we can find the range, the horizontal distance. So that's one of the key equations. I think you start writing that down straight away. The distance in the x direction, or the range, which we're calling the horizontal distance in this case, is the initial horizontal velocity multiplied by the total time of flight. So the first thing is to get that time of flight. How do we do that? Well, we know it will, as it jumps, it'll do this sort of shape, and it'll take half the time to reach the top of its flight. So this will be the point which we use. We break it in half. We can find the time it takes to reach this point here. And then multiply that time by 2, because that of course will be the time that it reaches the ground again. And to do that we need to use a kinematic equation and focus on the vertical component of the velocity. We know that that was given to us as 5.5 meters per second. All the time that it's moving upwards in this first part of its journey, gravity is acting down, acceleration due to gravity, so we can take that as negative 9.8 meters per second squared. So I think the easiest equation would be the final minus the initial of acceleration equals the time. So plugging that in, this of course is half of the time of flight to reach halfway up. So that's 0, final velocity is 0, initial was 5.5, and acceleration is negative 9.8, which gives us half the time of flight as 0.56122, 0.56122, to keep all the figures for the meantime, seconds. Multiply that by 2 to give us the total time t as 1.122, and then we multiply that, as I mentioned, we multiply that by the 6.8, the initial velocity vector, 6.8 times that 1.122, and we find the range dx. Sorry, this is a bit messy now. Dx equal to 7.6 meters. So check your own answer, and if you got this correct, the entire thing, it's worth an excellence. If you attempted to calculate the time in the air with a minor problem, for example not doubling, and you only use half the time of flight, you still got achieved no, in fact you could have got merit if that was the only error. But if there was some other error with the time calculation, but you still knew to use that time to multiply against 6.8, you possibly just got achieved. Okay, question 4. We're told about gannets flying in circles to feed. One particular gannet is flying in a horizontal circle, radius 22 meters and a constant speed of 3.3 meters per second. Calculate the acceleration of the gannet. So the question is, which equation applies given the radius and the speed? Hopefully you'll recognize it from the formula sheet if you have one handy. Acceleration, centripetal acceleration equals the speed squared over the radius. So plugging in the numbers, 22 squared divided by 3.3. Nope, that's wrong. Sorry, other way around. Yep. 3.3 squared over 22. That's correct. That gives us 0.50 meters per second squared. Another typical question, given a diagram as follows, you are asked to label the acceleration in this case and velocity of the gannet at that particular position shown. So the velocity, of course, is this way, perfectly tangential to the circle, and the the acceleration must be towards the center of the circle. So you'd label it as follows. Possibly even better to put a 90-degree angle symbol between those two vectors, showing that you know that to be the case. So here's another typical question of circular motion. Explain how it is possible for the gannet to be accelerating even though the speed is not changing. You should refer to the definition of acceleration in your answer. So this kind of question, starting with that idea straight away would be a sensible thing to do. Here's the model answer. Acceleration is change in velocity divided by change in time. Show the formula. The gannet's speed is not changing, but since velocity is speed with direction, this is the key point here, and the gannet is constantly changing direction because it's moving in a circle, its velocity is changing, therefore the gannet is accelerating. So 1, 2, 3, those three ideas must be there, must be communicated no matter how you did it, but the logical order would be probably this one, starting with definition and then explaining why velocity is changing even though the speed remains constant.